Test.
If we don't have it, we're not buying it. Yeah.
And you can say that we have a speaker who has agreed to do it for a very reasonable price.
Yeah.
Friends and family discount.
Okay, I will,
And then we can talk more about how actually, like, I'm just with everything, because I just signed the 76 or whatever the form is for the province, which is something they have a very large check, an annoying check, for probate. So the lawyer said, okay, that's like, they're coming back in 2 days.
yeah, I will go through that myself.
But I think doing this as a bill, that we don't, it will send the wrong message. There will be a breaking from funding, and there's always a breaking and other things.
Yes, sir. Yeah.
So, yes, I'm willing to help with it.
Yeah. Okay, so let me just speak to John again.
Yeah.
But just,
So, yeah, how do future, and it really is, partner with Jenny, I don't want to see, because they know how to raise money.
okay.
That's a double negative.
Okay, yeah, but you know what I mean. And the issue is that we
But
don't have.
their foundation, knows.
Their foundation.
That's what I mean, their foundation knows.
But David, really has to know, and none of it. So,
Yeah, and that takes some time to develop.
Or do you want well,
So here's the thing. I know enough people in that industry, pull people together a little bit. Talk to us, advise us, maybe increase, depending on some points that but who would be able to give an idea of that. And I know a person who would be the perfect director of science for these guys. And she has experience running big contracts, massive contracts with us.
which is good to have. Yeah.
So, he was like, what, where she is? First year, what?
No, we're at the museum.
1 minute long, if you want to take your seats.
How fast do you sit down?
Oh, good evening, everyone, and welcome to our August 7th edition of the Ottawa Centre meeting of the Royal Astronomical Society of Canada. I'm Jonathan King, Assistant Chair. I'll be emceeing tonight in Paul's absence. There we go. We are recording this webinar for posterity, as well as the fact that there are a number of people online this evening. For those who are online, please use the Q&A to ask a question to the speaker. Chat box comments can be seen by all, and raise your hand is disabled. And a big welcome to everyone who's here in person, online, from other centers, members of the public. Welcome. We acknowledge the trust placed in us by our First Nations with their ancestral lands and skies, and being able to look at the beautiful evening and night sky just as they have for many thousands of years. All right, tonight, our program, myself, introduction, new members, membership, Ottawa Skies for August. Dave Chisholm will be speaking to that. We have an excellent presentation from Jim Thompson this evening, who will be presenting his attempt at classic solar science. Looking forward to that one. We'll take a short break. After that, Simon will be doing a Rorschach, and man, I can have a hard time saying that word, test with astronomical stuff, so that's going to be pretty fun. We've got our observation reports, Richard Taylor, our monthly observing challenges. I believe I'm speaking to that in Richard's absence, unless he's here tonight. I don't think he is. And then I'll be closing up. Welcome new members. We had 6 new members in July. Are any of them here this evening in person? Yell out if you are. Don't be shy. No? Maybe they're online. We've had 37 new members so far in 2026, which is fantastic. And we've got some members in the news. Deborah Saravollo, our former president, who's now living in beautiful British Columbia, took this beautiful shot of the sun through wildfire smoke out in BC. Not great that they're having wildfires, but beautiful picture. Many thanks to Deborah for this one. All right, so Ottawa Skies for August. Dave's going to come speak. And Chris, can we get the house lights on? Dave's going to do a quick survey here to start off.
So before I get into the Ottawa Skies, we're initiating a discussion about our annual dinner meeting, which is normally held in November. Right now, we don't have a vice president, so I have to twist somebody else's arm to give me a hand, and I want to make their job easier. And I just wanted, by a show of hands, if we were not to get door prizes, would that keep you away? Nobody's putting their hands up, so maybe that will make the job a lot easier for the person who's coordinating that. And maybe online, Chris can collect the comments there. Okay, thank you. So we'll move into the Ottawa Skies for August. This is the month of eclipses. There we go. So the phases of the moon, we've got the new moon on the 12th, the full moon on the 28th. And on the 28th, there's a little nibble out of the moon. We have almost a full lunar eclipse. It's going to be pretty spectacular. And on the day of the new moon, on the 12th, we have a partial solar eclipse. I'll get into the details for those. Of course, we have the Perseid meteor showers overnight from August 12th to the 13th. And it's going to be very good this year because that happens to be the same time as the new moon, so you'll be able to see them quite well. So the partial solar eclipse is this Wednesday. You're going to be able to see it from Ottawa. Middle of the day, starts at 12:49, finishes at 2:33. Maximum eclipse is at 1:42. A few of us are going to be out here at the museum with our telescopes for the general public so that they can watch it. Time to dig out your eclipse glasses from the last solar eclipse that we had here. This is a video of what you're going to see, sped up 500 times. Not quite as spectacular as April 8th. There we go. So that's what you're going to see on that day. A couple of things when dealing with solar eclipses, just a reminder, if you have a telescope that has a sun filter in your eyepiece, you should never use that. It's very dangerous. What happens is the focused sunlight hits that piece, cracks the lens, the next thing you know, you're looking at the sun magnified many times and serious eye damage. There's different eclipse glasses available. We've got the really nice ones here, the wraparound type right there. And then you've got the paper type. Hopefully you've kept yours from your previous times. The only safe way to look at the sun through a telescope is to have a filter over the outside end of the telescope where the light comes in. And if you don't have anything like that, a little pinhole box, as shown here, is a good way to show the kids how the eclipse works. And I hit the wrong button. There we go. Never stare directly at the sun. Our eyes do not have any pain sensors. So while you stare at the sun, you may not feel any pain. But what happens is that the fluid at the back of the eye starts to boil over the retina. It ends up destroying your vision. So make sure your solar viewing glasses are certified. Don't go for the cheapest ones on Amazon. They may not protect your eyes. And again, don't look directly through a telescope or binoculars at the sun, and supervise children. Then on August the 28th, we have a partial lunar eclipse, and it's at a reasonable time too. It's only just a little bit after midnight when we reach the maximum eclipse, and hopefully we'll have clear skies for that night. Starts at 9:23, ends at 3:01. Again, here's a little video of what it looks like. Penumbral eclipse is pretty boring. It's when you get into the next stage. So we should be able to, given how much is covered there, the moon should turn red for us. So that's the maximum eclipse. Okay, and then it moves out. So for the sun, the days are getting shorter, as you can see from the rise and set times, and of course we have the partial solar eclipse on August the 12th. Folks in Spain and I believe Greenland and Iceland will see a full solar eclipse. Greatest western elongation for Mercury is on August the 2nd. Sorry you missed it, but you did get the astronauts a little while ago. It's furthest away from the sun, so you can see it just before sunrise. Looks like a little pinprick of light. Venus is visible in the early evening, first half of the month, and Mars is visible before sunrise right now. Jupiter's not visible. It's rising and setting with the sun, basically. Saturn's visible late evening and through the night. And Uranus is visible before sunrise, and Neptune is visible late evening and through the night. And here's our cartoon of the month. There we go. I got married before I bought my telescope. So.
Thank you, Dave. Maybe we can all chip in for you there. So it's an exciting month in the skies with both a solar eclipse, a partial lunar eclipse. The Perseids on the 12th, and there's kind of if you did the math with what Dave was going through, there's kind of a parade of planets on the 12th too when the sun comes up. So lots to look forward to. And for those of you who do want to look at the sun, the cardboard box viewer is really a safe way to do it. It works really well, and the perfect box for it is that nice long cardboard box your telescope came in. Works out really well. All right, so our first speaker this evening will be Jim Thompson. I believe you're here, Jim, right? Oh, he's going to be online. Okay, so Jim will be joining us online and telling us all about his fun with solar telescopes. So over to you, Jim. Thank you.
All right, thank you, John. I will share my screen. Oh, I need to send a request. All right, you should see on your screen my cover slide. So, welcome everyone to my attempt at classic solar science.
Sorry, Jim, can I ask you to hold for a second? We're not hearing you in the theater.
Okay.
No, then it's a matter of resetting this. Hit it. Audios. Yep. Okay, try now, Jim.
Okay, testing. 1, 2, 3. Testing.
Yeah, it's all good. Go ahead.
Check 1. Okay, excellent. Well, welcome everyone to my attempt at classic solar science. In this talk, I will share with you what happened when I pretended to be a pre-20th century solar scientist. The question I wanted to answer with this exercise was, can I use modern amateur equipment to confirm the observations made by the pioneers of solar science? This talk will take you through the data collection and reduction processes that I used in my attempt to answer this question. There are 4 specific classical observations that I have attempted to reproduce, including the Earth's orbit is elliptical, the sun rotates on its axis with the speed varying by latitude, the sun's activity varies on an 11-year cycle, and there is a repeatable pattern to sunspot location over the course of a solar cycle. Let's talk a bit now about how the scientists from the 17th, 18th, and 19th centuries made their solar observations. The most common method was to use a telescope for rear projection. This was a relatively easy and safe way of observing the sun and sketching what can be seen. And in fact, you could use this method for the upcoming eclipse. Early on, telescope optics quality was poor, so most sun observations were made using slow focal ratio refractors. The image at right is a reproduction of the type of scope that was typically used, made by Ken Spencer. The telescope he made has a 1-inch aperture with a 1 meter focal length, giving an f40 focal ratio. Over time, optics quality improved, allowing for better resolution observations. In the 1830s, John Herschel came up with the idea of the solar wedge as a way of diverting the bulk of the sun's energy, making it safe to directly observe the sun with a telescope. This is my preferred method of observing the sun in white light, with the wedge made by Bader Planetarium being the unit that I use. Here are a couple images of my white light solar observing setup. I have used a number of different arrangements over the years, but this is my current backyard setup at home, which gets the most use. The main telescope I use is a William Optics 98mm aperture refractor with a native focal ratio of f6.3. On the back of that, I have the Bader safety wedge, in this case, the photo version, which does not have the permanently installed neutral density filter that the visual version has. And this allows me much shorter camera shutter speeds. When observing in white light, I usually add a narrow band filter to improve contrast and sharpness. Most often, this will be a stack of 2 calcium 2K filters, one by Bader and the other by Omega filters. Their combined band pass being around 2 nanometers wide. Finally, the camera I have been using for the last couple of years is the imaging source DMK33UX226, which has tiny 1.85 micron pixels. Very recently, I have switched to a new camera, the ASI 676, which I released a YouTube video on a few months ago. One interesting thing to note before we move on is how low in the sky my telescope is pointed in this particular image on the left. The photo was taken during a mid-December session at around noon local time. Because of my location at 45 degrees north latitude, well, I guess all of our locations, this is as high as the sun gets for this time of year, adding an extra challenge to observing in the wintertime. A few of you may have noticed that I said I often observe the sun using a calcium 2K filter, and are wondering to yourself, why? My objective is to observe and analyze the sun's activity, which classically means observing sunspots. Here are 3 images of the same sunspot group captured in April 2023. Each image was taken using a different wavelength of light, as noted. Scientists using rear projection or Herschel wedges would have been observing the whole visual spectrum, what some call the solar continuum. This is a view of the sun's photosphere where most of the visible light is coming from. I have instead decided to focus my observations on calcium 2K because it not only shows sunspot activity, but also the extensive, brightly illuminated plages that surround them. Plages are a more consistent representation of the sun's activity level, and they are best observed using calcium 2K light. When I started digging into my computer archives at the beginning of this project, I found that I have made quite a few observations of the sun over the years. I found 56 high-quality full solar disk observations using calcium K, captured between January 2019 and January 2026. Prior to that, my observations are less consistent, either being only of part of the solar disk or not being made using calcium K. These other earlier observations go back to September 2012, when I was just getting back into amateur astronomy. So the quality of these images pales in comparison to what I can achieve now. Nonetheless, I was able to find 44 of these lower quality observations from which at least some data could be extracted. As you can imagine, the telescope mount and camera used for these 100 observations varies, which added some complexity to my data reduction process. There were also variations in seeing, camera exposure, optics behavior, and limb darkening, resulting in my needing to come up with some way of flattening the images after the fact. This is an example of one of my 56 high-quality solar images. It was created by stacking the 200 best frames from a capture of between 2,000 and 4,000 frames. Stacking was done using the free software AutoStackert, with sharpening applied afterwards using another free software called IMPPG. Both of these are readily available online. My image calibration started with using the image archive at the NASA Solar and Heliospheric Observatory website as a reference to correct the rotation of each image, making sure the sun's equator was horizontal. I then adjusted the tone of each image so that they were similar to each other. Then I began the process of constructing a synthetic flat frame for each image. To do this, I used a clone tool to manually remove details like sunspots and plages. Then I applied a 100 pixel Gaussian blur filter. I found that I got a better end result if I then scaled this blurred image up by 5% before applying it to the original image as a flat. Here is what the end result looks like. The limb darkening has been removed from the image, along with any other non-uniformities, allowing for a much easier analysis of the sunspots and plages. This process was repeated for all my images, so 100 times. With my image calibration completed, it was now time to start answering my original question. The first observation to verify was that the Earth's orbit is elliptical. In 1609, Johannes Kepler proved that planetary orbits are ellipses with the sun at one focus. He made this discovery when he was attempting to formulate the equations of motion for Mars using the very accurate observations made by Tycho Brahe. Kepler found that Brahe's observations didn't fit a circle, but they did fit an ellipse. Kepler also observed that the sun's angular size as observed from the Earth varies over the course of the year, suggesting to him that the Earth's orbit is also an ellipse. To verify this observation, I simply needed to back out the sun's angular size from each of my images. I did this using the sun's size in pixels from each image, combined with the camera sensor's resolution in arc seconds per pixel, which I calculated from the camera sensor pixel size and telescope focal length. Using the online calculator at astronomy.tools, I was able to do these calculations. The result of my calculation is plotted on this graph. My data clearly shows that there is a variation in angular size of the sun, with my measured period, phase, and amplitude all matching the accepted values very well. I do, however, seem to have a 0.1 arc minute offset in my measurements. I looked at the sensitivity of my size calculation to the accuracy of my input values and found the following. The sensitivity to the number of image pixels is low, with only about 0.01 arc minute error for every 1 pixel error from the image. Sensitivity is moderate to telescope focal length, with 0.05 arc minutes of change per 1 millimeter of focal length, and sensitivity is high to the sensor pixel size at 0.15 arc minutes per 0.01 microns of pixel size. So, I believe that the manufacturer round-off error in their reported telescope focal length and/or camera sensor pixel size can easily explain my 0.1 arc minute offset. The next thing to verify was that the sun rotates. Thomas Harriot in 1610 and Galileo Galilei in 1612 both reported observing sunspots moving across the face of the sun in the same direction. They posited that sunspots were fixed features on the sun's surface and that the sun must rotate. This observation is easily verified by looking at the sun on 2 or more occasions within a few days of each other. Here is my best example. 3 observations made within a 5-day period back in the summer of 2023. The movement of the sunspots from left to right is easily observed. A bit more subtle is the fact that sunspots closer to the sun's equator are moving faster than those further out. Here, let me add some lines that help you to see what I mean. This is called differential rotation, an important characteristic of the sun and a big part of the reason why there are sunspots at all. Differential rotation was first discovered by Jesuit priest and physicist/astronomer Christoph Scheiner in 1630 from his sunspot observations. The phenomenon was more precisely measured by famous solar scientist Richard Carrington in 1863. He found that the sun's equator rotates every 25 days, significantly faster than its poles at 36 days. This observation can be verified by an amateur if they plot the latitude and longitude of sunspots as they travel across the sun from day to day. The determination of a sunspot's latitude and longitude are determined using something called a Stonyhurst disk, named after the college in the UK where it was first used. This is essentially a grid that one overlays on their image of the sun. Because the Earth's orbital plane is not quite parallel to the sun's equator, a different Stonyhurst disk is required for different times of the year. The one shown here being for the month of July. For my measurements, I created my own Stonyhurst disk using CAD software. It is a hemisphere constructed of lines at 1 degree intervals. Here is an example of my Stonyhurst disk overlaid on top of one of my images. Using this grid, I tracked the movement of 13 different features over 5 days. I have overlaid my measurements on this plot from the Encyclopedia of Astronomy and Astrophysics. My measurements have captured the sun's differential rotation, with features moving faster near the equator than at higher latitudes. My absolute rotation rate, however, is about 9% lower than the accepted values. From what I have read, my error is likely due to the fact that sunspots are not, in fact, fixed to the sun's surface. They are able to drift and evolve separately from the rest of the sun, introducing an error. To get a better result, I simply need to collect more data to average out this error. By the way, if you're interested to learn more about the sun's differential rotation and how it plays a role in its activity cycle and the generation of sunspots, please feel free to check out my presentation, Anatomy of a Sunspot. The third observation to verify is that the sun has a 11-year activity cycle. The sun cycle was first reported by amateur astronomer Samuel Schwab in 1843. He used his own 17 years of observations to determine the sun's cycle was 10 years long. Inspired by Schwab's report, Swiss astronomer Rudolf Wolf compiled over 200 years of observations, including 40 years of his own observations, refining the solar cycle duration to 11 years. The numbering convention used by Wolf for each solar cycle is still used today, what we call Wolf numbers. Presently, we are in Wolf cycle number 25. My 100 observations are spread out over a slightly more than 13-year period, so in theory, I should be able to see an entire solar cycle in my data. To evaluate my data, I have compared it with the data that is hosted on the NOAA website. A live chart of monthly sunspot count is available there. To this, I compare my own daily sunspot count, the percentage of the solar disk covered by sunspots, and the percentage of solar disk covered by plages. Starting with my daily sunspot count, the data is highly scattered, making trends hard to see. I understand why the NOAA charts are only of monthly sunspot count, instead, to smooth out the data. Next, the sunspot area data shows a weak trend over the cycle, but nonetheless aligns pretty well with the NOAA chart. Finally, the plage area data produced a nice trend. Unfortunately, I only have 7 years worth of plage data, so I am unable to confirm the overall length of the solar cycle from this data. If I didn't already know that a solar cycle's length is supposed to be 11 years, I would say, based on my data, that it was more like 10 to 10.5 years. My observation is, in fact, consistent with historical data, in that the sun's cycle is not exactly 11 years. It varies from cycle to cycle. It is 11 years long on average. One interesting finding from my data analysis is that the area of the sun's disk covered by plages is roughly 20 times that covered by sunspots. This observation supports the notion that the net energy output of the sun is higher during periods of high sunspot activity. While searching the internet for material to put in this presentation, I came across this plot, showing historically how the daily sunspot area has varied over the past 150 years. My measurements of this particular parameter align pretty well with the historical data. From my data, it is apparent that the current solar cycle is more active than typical. Sunspot coverage as large as we've seen this cycle has not been observed since the late 1950s. So that's pretty neat. The last classical observation to verify is the pattern to sunspot location. In 1861, Richard Carrington discovered that there was a pattern to where on the solar disk sunspots appeared over the course of the solar cycle. Carrington's research was further refined by German astronomer Gustav Sporer. It was found that at the start of a solar cycle, sunspots appear predominantly at higher latitudes, and as the solar cycle progresses, sunspots appear at lower and lower latitudes. When sunspot latitude is plotted over the course of the solar cycle, you get what is now referred to as a butterfly diagram. When I plotted the latitude of all the observed sunspots from my 56 high-quality images, I was able to produce the same butterfly pattern, confirming this classical observation. So I found that pretty neat. Well, that is it for my adventures in classical solar science. Before wrapping things up, I think it is worth mentioning that solar observing is a very rewarding pursuit that I highly recommend to fellow amateur astronomers. Solar Cycle 25 has been filled with no end of surprises. Just the dramatic change in activity from the start of the cycle to the peak, which came around the summer of 2024, is a sight to behold. I am eagerly looking forward to what new surprises our sun has in store for us next. So in summary, I was able to confirm that the Earth's orbit is elliptical. However, I did encounter an offset in my measurements that I believe are due to round-off errors in the OAM reporting of telescope focal length and/or camera sensor pixel dimensions. I was able to confirm that the sun rotates, and that the rotation is faster at the equator than at the poles. My measured rotation rate was roughly 9% too slow, most likely due to sunspot proper motion and evolution. More observations are required to reduce this error. I mostly confirmed that the solar cycle is on the order of 11 years long. My data suggests 10 to 10.5 years, which is consistent with the historical variation in the solar cycle duration. I found that using daily sunspot counts gave very scattered results. A monthly count would be better, which means way more frequent observations. Sunspot or plage area also appears to be a good metric for tracking the solar cycle. Finally, I was able to confirm the sunspot butterfly pattern. To be honest, it took a lot of work to turn all my raw images into usable data, but I did have a lot of fun doing it. Well, that concludes my talk today. If anyone has a question, I would be happy to answer.
All right, let's start with the audience. Anyone got a question for Jim? Over there? Okay. Can we get the house lights on a bit, Chris?
Hi, Jim. You mentioned
Hi.
about the Wolf numbers, and yet what you see published are usually called Carrington numbers. Or I guess they're the same thing. Oh, Carrington cycles.
Yeah, but as with many discoveries in science, there is often contention about whose name gets put on the discovery. Carrington being the first, a very prominent scientist who had many discoveries in solar science, is often attributed to many of those different parameters that we use for tracking the solar activity and features on the sun. But from what I read, it was Wolf who defined it for the first time.
Okay.
Anyone else in the audience?
Jim, what defines what one sunspot is? So if I'm looking at the one in the middle and I'm to count those, how many am I seeing? And what criterion do you use to say that's one sunspot or that's 5 sunspots?
That is an excellent question, and I don't have a really solid answer except that I just used my own personal judgment. When you look at what these little black specks that don't have a penumbra around them, they're not called sunspots. They're called what are they called? Pores, I think, or something like that. So I only counted what had a penumbra around it. But like as you say, over this clump here that's on the left, like is that 1? Is that 5? Is that so? There is definitely some variation in the interpretation of what's a sunspot when you're counting them. Absolutely. I think that as long as one observer is consistent with themselves, then the trend should be reliable. That, in my opinion, anyway.
Okay, thank you, Jim. Anyone else in the audience before I go to online? Oh, we got another one over here. We'll take this one more and then we'll see about online.
Thank you. That's the automatic seats. Yeah, thanks, Jim. How did you actually calculate the area of the sun that was covered by sunspots, plages, so on?
So yeah, that was part of the laborious data reduction process. So one of the main drivers for flattening all of the images was to get as even an illumination across the disk, and that then allowed me to just simply do a histogram analysis. So count all of the pixels above a certain brightness and say those are plages. Count all the pixels below a certain brightness, call that sunspot. So once I had those images flattened, and there was a little bit of tone mapping as well to really make it clearly defined, okay, this is plage, this is sunspot. It was just a simple matter of dumping out the histogram and pulling out the numbers, the pixel count on the bright end and the dark end.
Great, thank you, Jim. Chris, do we have any questions online?
No, we don't.
All right, well, thank you, Jim, for your excellent presentation. It was very illuminating.
Thank you.
Yeah, my jokes are pretty bad. You better get used to them. When you're ready, Chris. All right, at this point, we're going to take a short break. It's 10 after 8, so let's plan to be here back at 8:25, so 15 minutes from now. Thank you.
This is my thesis
We'll get going in just a couple of minutes here, folks. You've got 1 minute. Okay, Chris, we'll get going. All right, let's carry on with our second half. We're going to talk a little bit about benefits of joining the society. The biggest benefit of all is all the cool people you get to hang out with, all the other amateur astronomers who are in various stages of their journey of how do I put this telescope together to right up to analyzing sunspots and you name it. It's quite a great club, and certainly encourage anyone who has interest to join up. We have a number of specific benefits. We have our Ted Bean Loan Library, which is an excellent way to try out different types of telescopes before you actually buy, and you're able to sign them out just like a library book. We do have a library as well. I'm not sure if our librarian's here tonight. Hey, our librarian's here tonight. So if you're interested in signing out a book at the end of the night, come on down and we'll show you the library. As well, out at the Milliken Tail, we have the Fred Lossing Observatory with 3 fixed telescopes and a number of mounds for people who want to bring their own telescope. The site has been there for a very long time and is quite well set up, and certainly a place to really get a good look at the night sky. As well, we have our Astronotes, our monthly newsletter that comes out electronic to all the members, the RASC Journal, bi-monthly, and as well, you get an annual hard copy of the Observer's Handbook, which is about everything you're going to need to know for reference material as an amateur astronomer. We also have our Discord server, which a lot of the members are very active on. You'll see some observations here a bit later tonight, but there's a lot more that goes up on the server, and there's a lot of great information exchanged on all sorts of astronomy topics. As well as a member, you get a copy or access to a copy of Astros. I have such art. Thank you, Astrospheric Pro, which is great for predicting the weather. And if you know, lately in Ottawa, seeing the sky at night is always a challenge, it seems these days. Membership. Regular membership is $118 for the year. Family membership, which if you want to have all of the family be members, $112.50 base fee, plus $18 for every adult and $10.50 for every youth. Youth membership, if you're under 21 years old or under 25 if you're a student, is $77.40 a year. And when you think about this, this is really quite reasonable, especially if you go out for dinner these days. All right, so coming up, we've got Dr. Simon, who's going to introduce us to the brand new topic of astropsychiatry. Over to you.
All righty. Well, you're not used to me getting up here and talking about deep sky objects. Usually I'm talking to you about something to do with a planet or the moon or something. But as amateur astronomers, we all look up at the sky, but as human beings, we tend to see what we've been trained or told to recognize when we do look.
Now, astronomical objects, especially the bigger and brighter nebulae, commonly carry nicknames. While some are pretty obvious, that's right, I've got to do something here. Am I hitting the right one? The big green one. There we go. Like NGC 281, the Pac-Man in Cassiopeia. Yeah, I think everybody can see the Pac-Man there. But others defy explanation. I offer as an example NGC 1491 in Perseus, the fossil footprint. I've seen a lot of fossils as a geologist. I've seen some fossil footprints, but that isn't what that looks like to me. Now, remember, many of these names were actually designated, perhaps while people were looking more through their telescopes with eyepieces, visually observing. But since then, we've gone digital. We've got much wider fields of view on mini refractors. And I think we've got a different window that we're looking through. Now, when it comes to observing personally from my Bortle 9+ backyard in downtown Ottawa, I'm a big fan of electronically assisted astronomy. Using a camera to live stack. I live stack about 20 to 30 second frames. And then I'm watching the image developed on screen over a period of about 10 minutes, probably not much more than that. But that gives me the time to look at the target object as it develops on screen and to ask myself if it really looks like what the astronomy literature tells me I should be seeing. But here's the question I'm asking tonight. Does what I think I see in a deep sky object reflect more on the object, or does it reflect more on me as a person? In other words, are deep sky objects the astronomical equivalent of the ink blots in a psychologist's Rorschach test? I can pronounce it. Now, just for those who don't know what a Rorschach test is, you have flashcards and you have this ink blot. I'm not going to tell you what it looks like because that's the whole point of the test. And the psychologist will flash these things at you and say, what's the first thing that comes into your mind? And you'll say, fossil footprint. And at that point, you'll probably be written off and put in a psychiatric hospital. However, here's my question to you tonight. How would you perform on an astronomical Rorschach test? Let's find out with a few selected examples from my personal archive of images. This is a night for image archives. Jim just showed us his solar image archive. I'm going to be showing you a few things from my deep sky objects. Now, this will be fast. So don't worry about the fact that there are 31 images. This will be fast because Rorschach tests are based on flashcards and instantaneous reactions. So, are we ready? Let's start with something easy. NGC 7380, the Wizard Nebula in Cepheus. I'm just waiting. I'll tell you, not only do I not see a wizard, I just see a galactic cloud and nothing else. I think that qualifies me as psychologically normal. Now, Jim Thompson, Jim, you listening, has tried to show me the wizard several times. He's even drawn it for me. But I just do not get it. I guess I never will understand this one. However, I'm not completely devoid of imagination. Here's the Veil supernova remnant in Cygnus. Now, there we go, good. Now, I can see the witch's broom. I can see Pickering's triangle, all the way down to there. And yeah, I can see this part. But I'm fixated on that eastern part, which to me is a dead ringer for the face of the alien from Ridley Scott's movie of the same name. Don't believe me? I'm pressing the wrong button. Hang on, there, I'll get it right. There we go. Yeah. Tell me you don't see the alien. All righty. Now, I have to warn you, there is a qualified doctor of psychiatry, psychology, I'm not sure which one it is, Jim, in the audience who may actually be analyzing your reactions tonight. All right, let me get the right button. So, okay, let's take some really simple ones that you all know well, you've looked at 100 times. M1 in Taurus. Who hasn't looked at the crab? Crab? I don't see a crab. Never have. Don't really understand why anybody thinks there's a crab, but I do see an amoeba. Maybe. M8 in Sagittarius. We love to look at this. We call it the lagoon. But I don't know where the lagoon is, but what I do see, I see a man's face. There's his hair, there's his head, I see his eyebrow, eyes, there's his nose. I think he's singing. I'm not crazy. M16. We love M16 in Serpens Cauda. The eagle. I agree, the eagle. But which eagle? Well, it's actually that one in there. But that, of course, is what you would see through a nice eyepiece, high-power eyepiece, looking optically. But when you can actually put together a mosaic, I would say that this could also be the eagle. It actually looks like the seagull, but we're not going to go there. If you don't know what the seagull looks like, let's keep it that way. M17 in Sagittarius. I love this. The Swan, or Omega Nebula. Well, people used to think there was a swan in there. Okay. Body and a neck. I still can't see the Omega. But when I get a wide field of view like this, what I see is an upside-down tree. There's the trunk. There are the branches and the canopy. And there's the root system. Or maybe you think it's a spider's web, just this part here. We all know about the psychology of spiders, don't we? Okay, NGC 7000 in Cygnus, the North American nebula. Yeah, okay. The idea is this is Florida, Gulf of Mexico, Middle America, Pacific Coast, Canada, that's us. But we've missed out on the territories up here. They've disappeared, and so has Alaska. Or you can see what I see, an angry man shouting. There's his nose. He's a boxer, by the way, so there's his cauliflower ear. This is his mouth. He's wide open. These are his teeth, which he's exposing. And he's really yelling at this poor pelican. Did I say pelican? I see 5067 in Cygnus, the pelican. Why not? I can see the pelican. I see the big beak. I see the eye. I see the boss on the top of the head, the wings. It's a beautiful pelican. There's no doubt about it. But what happens when you're looking with your German equatorial mount? Your camera's on the other side from where you usually see it, and you get to see this perspective on the pelican. Pelican or a rabbit? Big floppy ears, eyes. However, what happens if you pull up even further back and get a wider field of view? If any of you have taken your kids to the Museum of Nature recently, there's a dinosaur with the big horn on the back there. Next time you look at the pelican, think about this. The Sol Nebula, 1848, in Cassiopeia, I think that is underneath there. I don't know what a soul looks like. So this could be a good representation of the soul. But what I actually see, I see a baby. There's its head. It's on its back. There's the arm. There's the legs. You know how they get their legs up and they can sort of put them in the mouth? So, yeah, I could see a baby, maybe, or a goldfish. Is there something psychologically wrong with me that I can't tell the difference between a baby and a goldfish? I hope you can see the goldfish. Whoops, I didn't want to do that. How do I go back? The little other button. The little button below the big green button. Oh, hey, somebody did it for me. Thank you. You've got the big tail, you've got the dorsal fin, the big tail, the eye, it's swimming that way. I see 1396 in Cepheus, well known as containing the elephant's trunk. I'll come to the elephant's trunk in a moment. The elephant's trunk is sitting in here, but it's actually sitting within this vast bright nebula. And what I see in that bright nebula, I've never seen a name for that bright nebula, but I'll tell you what I name it, the lioness's head. There's an ear, two eyes, flat nose, mouth, and she's looking that way at game that she's hungrily about to hunt. But if you go in and you look at the elephant's trunk itself, that's supposed to be the bump and the forehead, and then the trunk somehow comes down here. I don't know what it's supposed to be doing down there. I do not see an elephant in there or an elephant's trunk. But if I turn the picture around, what I do see is a racehorse in full tilt. There's its muzzle, there's its one nostril, there's its forehead, there's its eye, and there's its ears flat on its back, and it's charging to the left. NGC 2174 in Orion, the monkey's head. Yeah, I can see a monkey. Can you see a monkey? That would be the eyebrow ridge, the eyes here. That would be a kind of a snout. The mouth would be described like this, and a bit of a chin. And that would be the back of the head. What happens if your camera actually gives you the image upside down? Well, I see either a Neanderthal or another monkey. There's the eyebrow ridge, there's the eye, probably the ear over here. The mouth is now down this way, and there's a bit of a chin. So it all depends on which way up you think everything is. How's your geography? NGC 1499 in Perseus. This is the California Nebula, supposedly. So San Jose, Los Angeles, San Francisco, getting up towards here, Canada. Maybe. I think this is a pretty good representation. That eye is right there. Those tentacles are right here. And the body with the, well, I'm not quite sure what that's called, but I guess it's a lateral fin, that's up there. To me, that's far more of a cuttlefish than it is California. I tried telling my wife this, and her daughter lives down in California. She knows all about California, and she looked at me and said, no, it's California. DWB 111. You've never heard of this. It's called the propeller, and it's in Cygnus. And the propeller's hiding over here. It's really just a bright part of this really extensive filamentous nebulosity. And people make a big to-do about that part, and then something like that. But I find it's, well, the first time I saw it, I was disappointed. I was expecting to see a propeller. So when I actually took an image really quite close in, there's the propellery thing. This disappears. It all becomes part of this stuff out here. What I see there is either a big fat worm, or a snake, or maybe it's a basket of snakes. But I don't see a propeller. Try this again. There we go. I love IC 405 in Auriga, the flaming star. I love to observe this object, never get tired of it, but I have no idea why it's called the flaming star. There are lots of flaming stars in there, I'll buy that. What I see is a dragon's head. You know the Chinese dragon? You know, with the spiky bits on the top, and then the rest of the guys are in the tube back here. I see that, but I don't see a flaming star. This over here, by the way, is called the tadpoles, IC 410. Well, if you actually focus in on the tadpoles, that doesn't look like tadpole to me, or tadpoles in the plural. The tadpoles are these two little bright spots there are the tails. This one they could not have named using visual observation, so they really have no excuse on this one. So I don't know what I would call this. It just looks like a very nice nebula with bright parts and dark parts. Okay, well, we'll give it that name officially. NGC 6888 in Cygnus. Everybody loves the crescent. And you can tell why they thought it was a crescent, because when you observe this through a telescope with eyepieces, what you essentially see is this bright exterior here. Brighter here, less bright there. So yeah, it looked like a crescent. But now with modern equipment, cameras, etc., and processing, you can do so much more to it. So you actually get to see all this interior stuff. And it's like cellular. Cellular? Cellular. Yeah. I figure a cauliflower, that's between you and me. Okay, this one is a difficult one. I hesitated to put it in, then I decided no, I had to. This is IC63 in Cassiopeia. The first time that I saw it, a number of years back, all I could see was this, and it was very dim. But I was so pleased that I could even see it against its star field. And then more recently, equipment has improved, my processing has improved, and now I've got this thing and this incredible tail here of nebulosity behind it. And I don't know why one would call it a ghost, other than the fact that through an eyepiece it's very difficult to see and very faint. What? Oh, no. How did it go back again? Do I have to press that red thing? Yes. Good. Okay. This looks to me like a drone with an exhaust tail. Now, maybe that's because I've been watching too much bad news these days, but that's what came to my mind. That's an illustration of how the world affects us psychologically. And then this one here, NGC 2024 in Orion. I'm talking about this part. I'm not going to mention this part. You don't need to mention this part in a Rorschach test. It wouldn't be fair. Does anybody not know what that is? No, good. So, okay, the Flame Nebula. Flame? Come on, Canada. It's a maple leaf. Tell me that's not a maple leaf, Canada. All righty. Okay, so we come back to NG7380 Cepheus Wizard. I'm really never going to understand this one. And from the reaction you had at the beginning of the talk, I don't think there are too many people in the audience that see too much of a wizard in there either. Did I mention 1491 in Perseus, the fossil footprint? I think I did. So, I always end my talks with what is my take-home message tonight? So here's my take-home message on this one, tongue-in-cheek. Next time you're out and observing, especially if you get to observe the sharpless objects. The sharpless objects are a number of nebulosities like this. Some of them are rather small, some of them are rather faint, but some of them are gloriously large and bright. None of them have names, except for some of the classics. The Bubble Nebula happens to be one of them. Turns out the Crescent Nebula is one of them, but all of the others, there's about 300. And they have no names. So it's tabula rasa. You can call it what you want. And what would be really interesting is if people take images of those things and show us and tell us what they think they're going to call it. And then we'll know how the Rorschach test has worked for you. Thank you very much. Did I get my doctorate in psychology?
Yeah, he's got another degree to his credit now. Does anyone have any questions on this one? No, I can't really see. No. How about online, Chris?
Just a comment from Andrew that he does see the wizard. So everyone's different.
Sorry, Chris? Oh, someone sees the wizard.
Yep.
Yeah, I'm struggling to see it, but thank you very much, Simon. All right, we're going to go into our observation reports. We've got 6 people tonight. We'll start with Taras, and just a quick reminder, you've got 4 minutes.
Good evening, everyone. My first few slides about the event which happened early June was conjunction of Venus and Jupiter. This picture was taken in Fitzroy Harbor on May 30th. So the two planets, Venus and Jupiter, were about 10 degrees of arc apart, and this was just a nice scenery. I was actually doing some other project, but it coincided with time when this conjunction was about to happen, so I used my camera to take a few of these conjunction events in a row, and the second was on June 7, with the planets being only 1.6, if I'm not mistaken, degrees apart. This is again the very same area, Fitzroy Harbor, just beautiful place. It was quite dark, and I wanted to share this picture. The next one was next day, essentially June 8th, again about 1.5, 1.6 degrees apart. Quite dark place as well. I got some results for the other project from that place, which I'll be probably showing in the next meeting, but the scenery was just nice. And this picture is actually taken with the cell phone camera, so I was happy to get such result with relatively cheap equipment. And a few days later, I think this was June 15th, the planets were already much further, about 7 degrees apart, but this is again the very same Fitzroy Harbor with nice scenery. There's actually 3 planets here. This is, again, Jupiter going a bit lower now, so the Jupiter during the conjunctions move closer to the Sun, while Venus remained more or less in the same position. So at the closest approach, there were about 1.6 degrees, but this now is about 7 degrees apart. And the third planet is actually somewhere here. You cannot see it on this slide, but it has one more presence here on the screen, and that was Mercury. So I was imaging Mercury, and this is actually a close-up of this little dot. Not sure if it can be seen from the audience, so I enlarged it and increased the histograms for it to be seen clearly. And I'm not sure again, there is a little dot on the screen when I was imaging it. So this was the conjunction event for Venus and Jupiter, while there was another big event a little bit later. I think this was on June 17th, and namely that was conjunction of Venus and Moon in this time. Actually, the Moon was, or rather, the planet was supposed to hide behind the Moon and pass around 3 o'clock, starting hiding behind the Moon, which I wasn't able to image. So later on, around 5 o'clock p.m. on June 17th, was supposed to show from the other limb of the Moon. But this is what the day looked like. So there were clouds, and I didn't even have much chance to image the ingress of the planet. So yeah, this is, I guess, what, I'm not sure if, right. So this is the video of what my expected area where the planet would appear would look like. So there is a periods of time when the clouds would go away, and the expected area was somewhere here. You can't see much. So I was a bit disappointed. And now the exit or egress was supposed to happen at 4:56, 4:57. And this is the area, this is the time when the clouds actually came in. So a few minutes later only, I think this is now time to play the second video. Ta-da! It actually showed up when the clouds retreated, and I was quite happy to see that, but it was not for too long. So after that, the clouds came again until the planet was much further. So I was able actually to image the planet and Moon separately. Just the moment I was really expecting, hoping to see the moment when Venus would appear from behind the Moon, but unfortunately was not the case. So what I did, I combined the imaged sequences with the Moon and the planet separately. And as you saw from the previous slide, the Venus was way overexposed, so it wouldn't really be showing any details. I combined them separately and made this collage such a way that the position of Venus would exactly match where it was in the video. And again, having chance to image the planet, I put together slides from few observations on June 17th and 28th, when I imaged the planet in both visual and UV spectrum, with slight difference in size, which shows a bit more of physical size in these pictures because I used two different telescopes. So the larger one was imaged with the observatory's Star Master with around 2000 millimeter focal length, while this one was with my new Schmidt CAS of 1600 millimeter focal length. And again, I used the UV filter to image the clouds separately and then combine them into the UV image in combination with visual. That's it. Thank you.
All right, Paul, over to you. You want to drive, right?
So that's forward, and that's backward.
Good evening, everyone. I only have one image tonight, but this image is about 2 months worth of work. So I think we've saw it earlier tonight. It is the elephant trunk. So just to go on to what the other gentleman was saying there, I think to me it was upside down. So if this picture was bigger, I have another picture from a few years ago that when it goes down here, you can see the kind of the ears of the elephant, and that's the whole trunk going down. That's like where it picks up the water and things like that. So that's how I see it, right? So anyway, everybody with a telescope and a camera has done this one at some point or another. So basically, yeah. So it's in the constellation of Cepheus. It's, as we heard earlier, it's a part of IC 1396. That's the big emission nebula that it's just kind of at the end of Cepheus there. It's that whole emission nebula is about 100 light years across, or approximately 3 degrees. Right in the center of it is a big open cluster called Trumpler 37. And these are a lot of young stars. I forget the exact count now, but these stars apparently are less than 1 million years old, or maybe slightly older than 1 million, right? And about 2,400 light years away. So the actual, where is it? The actual, oh, I'm sorry, hold on. I have, try that again. That's what button I wanted. Yes, so the actual trunk itself is known as IC 1396A, or sharpless 131. I'm not sure if actually I got that right. I think this is known as a dark nebula. So that B stands for bright nebula. So that could be about the whole emission nebula itself. And the trunk is about 20 light years long, or about 1/2 degree, which is about a full moon diameter. So yeah, so this whole column of gas and dust now is basically like hydrogen alpha and dust and various other gases. Just up above, right here, there's a big star, and this is the star catalog number here, 206267. That's the one that's kind of energizing this whole column of gas, and the stellar winds and radiation are kind of carving this shape out, right? You can see right here it's starting to thin out here a little bit. So it's my understanding that this part up here is more what they call a dark globule, and this is a star-forming region in here. And there's been a bunch of infrared photography done, and apparently there's 2 or 3 protostars being formed in there. So you throw a few million years in, you're probably going to start to see this is gone, and you'll see more stars in the cluster. And then once this cluster gets going, I suspect the new stars are going to put pressure on this part, and that's going to become a star-forming region as well. So this whole thing is like a pillar of creation, similar to the Eagle Nebula. So next one, and just the dry stuff. It was taken through June and July, over a couple of months. It's an SHO image. Taken with my Ritchie Chrétien 6-inch, about 1,320 millimeters. I have a 2-tech camera with an IMX 294 sensor. And I use 2 filters, just a 5 nanometer Antlia HA03 and the sulfur 2 H beta filters. I'm sitting on an Ioptron 726 mount, and I have an off-axis guider with a IMX 662 two-step camera in there. My software is Nina, PhD2, Graxpert, and Surreal. And that is it. Thank you.
Jim, after our session with Simon, do you want to do this or do you want to do a group counseling session?
That was a lot of fun. I really enjoyed that. What do we see here? Okay. Well, during late June, while solar observing, I located 2 active regions that was getting a lot of publicity in the space news. Active region 4479 was considered a major highly active sunspot cluster on the sun that produced powerful X flares and M class flares, radio blackouts, and solar mass ejections in June and early July, before rotating out of view the west limb of the solar disk. So that's AR 4479, and along with that, the active region 4478 was considered a giant magnetically complex sunspot group, ranking one of the largest active regions of solar cycle 25, which is this current solar cycle. And this active region rotated into view in June. It features a massive size, and at that particular time carried a high potential of space weather impacts. Now, to get to the next one, is that right here? Okay.
That's hard.
Nope, it went back up. Okay, there we go, jumping around. Okay, and here we see these active regions on the solar surface of a wide-angle monochrome shot, showing an interesting and quite sizable prominence on the limb. And along here, okay, this is where my, okay, so right here, what we're looking at here are thin, elongated gas structures, or fibrils, which follow the direction and curvature of the magnetic field lines. And as a matter of fact, it's the pattern of fibrils that act as visual guides for mapping the sun's magnetic field lines and moving energy. Now, these structures over here, and this one, I believe this one as well. These structures look more like filaments, which are cool, dense plasma suspended by magnetic fields. And this is the same image processed with inverted light and color. And some folks use that and claim that there are some details that are enhanced with this particular method. And this is a compressed time-lapse, 45-minute animation of the prominence that we were just viewing, showing forward and reverse action. And what I'd like you to notice here, right along there, on the surface of the limb, notice how tiny, fast-moving jets of hot plasma, called spicules, shoot out up from the sun's surface continually. This was a day of low average to average seeing. Thank you.
Thank you, Jim. Over to the other Jim, and you're online.
Indeed. All right. Everybody can hear me all right? There's been a sudden technical glitch.
You're good.
So this is my new favorite thing. It is a mini refractor. I have it right here in my hands. It is tiny. It is 100 millimeters focal length and 1 inch aperture, 25 millimeters. And it is made by Tech, a Chinese company. And I had an opportunity to try it out up here at the Beach Bum Observatory. And the next couple of pictures that I'm going to show you were captured with this exact setup. So the GS100 plus an ASI 533 monochrome camera with the hydrogen alpha filter. So if you could go to the next image, please, Chris. So centered in the middle of this image is a nebula called NGC 6357. It is informally known as the Lobster Nebula, but also some people call it the War and Peace. If that's what you see, good for you. I refer you to Simon. At the bottom of the frame is the cat's paw, which actually looks like the cat's paw. It's another NGC nebula, and then above that is just a sort of a nameless, sharpless 2 object, just an area of excited hydrogen gas. So this field of view that provided by the combination of the GS100 and the ASI 533 is about 6.5 by 6.5 degrees. This particular image is looking very, very low in the south in the summertime. This is in the constellation Scorpio. And it's about, I think it was about 4 degrees above the horizon when I looked at it. That's how low it was in the sky. So very, very low. But using such a wide field of view really puts things into context. You can see, oh, wait, this isn't just a nebula in space. It's part of a much larger structure of dust and gas. Next image, please. Pardon me while I swat away the mosquitoes. Moving a fair piece north now. Some objects that we saw images of tonight. In the middle is M16, the Eagle, but zoomed way out. And in the lower left is M17, the Swan. Again, we're zoomed way out. And like I said, you can see that those 2 objects are not isolated in space. They are part of a much larger structure of dark, cold dust and gas intermixed with excited regions of gas that are lit up. So very cool to see it, the different perspective, in my opinion. A lot of fun. Next image, please. Continuing to move north up into Cygnus. This in the middle is the Tulip Nebula, which again, many people image and have lovely images of it. And also the crescent in the upper left corner. So Simon had a lovely image of that this evening. But zoomed in so you don't have the context that those objects are actually a small part of an enormous structure of emission, hydrogen gas, dust, star forming. It's a fascinating area with endless detail to explore, all in one big wide shot. Next image, please. Moving a little bit further into the center of Cygnus, we have IC 1318. I've talked about in the past. I personally see an Asian dragon myself. The bright star Saturn being the glowing eye of the dragon, but you can make your own judgment on that. And I can't remember, is there one more shot? There is, yes. The North American Nebula, which is right next door to the previous object. They are separated by a dark area you can see in the lower right called the Northern Coal Sack, which is a big blob of cold gas and dust. And you can see some of that cold gas and dust obstructing It's actually the North American and the Pelican are not two objects. They are one object that is obscured by this river of cold gas and dust that flows down into the northern coal sack, which is at the bottom. So very cool to see this all in the perspective gained from the super wide field of view of a mini refractor. I think that's it. Yep, great. Thank you.
Okay, we're back. Okay.
Okay, I seem to be the only one who worked on the challenge objects this month. Before I start, I just remembered that going back to the Rorschach test, the one that was called normally known as the Crescent Nebula used to be called Van Gogh's ear. I don't know who coined that one, but it looks like it, I guess, an ear. But anyways, this was the Challenge 2 object, an open cluster, and I forget what Richard called it. There was a name for it. But anyways, in moderately light-polluted skies, open clusters are some of the nicest things to look at because they punch through any, haze or light pollution in the background. Of these, I've got 4 of these challenge objects, and I don't think I had ever observed any of them. I'd have to go back and look at my notes and archives. But anyways, I thought that was a fairly attractive one. It was not big as open clusters go. Another challenge object. The next 3 are all planetary nebula. And the reason they get that name is that they tend to be small and round and look more or less the shape and size of Jupiter. They're usually maybe 1 to 4 arc minutes, not very big. But fortunately, they have a very high surface brightness, which makes them easier to photograph. And mostly they're the result of a low to medium mass star, which has reached the end of its lifetime, and it's just sort of puffing out its outer atmosphere, being impelled by ultraviolet light pressure from the interior, which has become very hot, and then the outer atmosphere is fluorescing from all that ultraviolet light. So here's the first one. This one was very tiny. I had to blow it way up, like crop it, because that one is only about 1 arc minute or less. Another one, this is another challenge object. This is in a very rich field. All of these, in fact, were in the constellation of Aquila, the eagle, which is nicely placed right now. That one, I think, if I had to name it, I'd call it looks like a little bit of a tomato, looking from the top. You see what looks like a little green stem and sepals on there. Oh, no, sorry, this one's a tomato. This one was the brightest of the bunch of them. Oh, and by the way, all of these were taken with my C-Star S50, which is only a 2-inch aperture, but still gives very nice results. And most of these were only 2 to 5 minute exposures. And then the last one was something I'd wanted to try for a while, but I just hadn't got around to it, just to see how far I can push the capabilities of the C-Star. Now this one was very low in the sky, only about 10 degrees right in the north, and I wouldn't have been able to find this if it wasn't for that there was a nice galaxy very close to it, NGC 3079, which is a rather irregular galaxy which seems to be having a lot of activity in it. But where the arrow is pointing is the first quasar that was discovered to be gravitationally split, that there's a foreground galaxy whose gravitational field acts like a lens, and it actually splits it in two. It's my scale here isn't enough to see the double part of it. I have seen amateur photos that have it double, but with a larger telescope. But the interesting thing here is its distance. The so-called redshift, the Z, is 1.41, which means it's expanding or receding from us at a rate of 141% of the speed of light. Now you think normally here the speed of light is the maximum possible velocity, but in this case it's not the light. It's actually the space, the universe is expanding, and that sort of expansion isn't ruled out by general or special relativity. So here it is expanding at 141% of the speed of light. Its distance, and this was what's known as the look-back distance or light travel distance, is approximately 8.7 billion light years. That number comes from a published number I saw from ESA, the European Space Agency. The thing is, the Z, the redshift, is something that can be measured directly. It's just how much the light wavelength has been stretched, and it's been stretched like 40% compared to its rest wavelength. But except for very low values of Z, it's not linear with distance. You have to use a complicated equation with 3 or 4 parameters. In fact, I was playing around with it. And you have to know the current value of the Hubble constant, which isn't, it's about 70, but it's not perfectly nailed down. The total amount of matter in the universe, which includes both luminous and dark matter, and the amount of dark energy. So all these 3 or 4 parameters in play, and they're actually calculators that you can play around with the values, and each time you do it, it gives a different distance, but mostly it lies in the range of 8 to 9 billion light years. But still, it's pretty amazing that the light that we're seeing came from that about 9 billion light years, or 9 billion years ago. There's a couple other quasars which are similar or even more distant. I'm going to be giving a try in the future. But that just shows with the capability of modern astronomical equipment. Now, this is a fairly simple 2-inch f5 refractor, but it's all fully automated and does its own image processing. So that's what you can get now with amateur equipment. I started out more than 40 years ago, actually close to 50 years ago in astronomy, and I never dreamed back then I'd be able to do something like this, image a quasar. In fact, quasars hadn't even been discovered at that point. I think it was in 1984 the first quasar was discovered. But anyways, that's it.
Okay.
Thank you very much, John. All right. I don't think Richard's here tonight, but these aren't his challenges, I don't think. Well, maybe they are. Well, summer beehive. Globular clusters. So, I think he's challenging you to try and get some nice shot of globular clusters.
No, Jonathan, these are his observations.
That was last month. Okay, so these are pictures Richard took. So, all right. So let's go back. Okay, dokie. All right, summer beehive. This is a picture Richard took, and it looks like he did it with his sea star. Came out pretty good. Then we got, oh boy, there's another word I can't pronounce. Ophiuchus globular clusters. Some nice pictures there. Rho-O. Oh, wow. I love that one. Okay, so last month you're observing challenges, which we talked about, with the constellation Aquila, NGC 6709 open cluster, Barnard's E-Dark Nebula, Planetary Nebula NGC 6781, 6804, and 6772, and the Solar System asteroid Juno. Gold stars were given to Xavier, Tony, and Mark for all their posted pictures of Bernard's. And Xavier also managed to get a picture of the Planetary Nebula NGC 6781. All right. This month's constellation challenge is the constellation Lyra. So your level 1 challenge is the constellation itself. Level 2 is Epsilon Lyrae, the double-double. Level 3 will be Messier 57, the Ring Nebula. Level 4, NGC 6675, which is a spiral galaxy. And solar system, you've got, of course, as mentioned earlier, the partial solar eclipse on the 12th and the partial lunar eclipse on the night of the 27th, 28th. So look forward to great photos of those on the Discord server and here as well if you want to do an observation next month. All right, public star parties. So next public star party is on August the 14th, with the rain date being August the 15th. And if we get rained out on both of those, it's the 21st or the 22nd. Really would love to see more volunteers. Our last public star party, we knew we had over 200 cars show up, so we're figuring about 350 people. Deepinder and I were managing the greeting side. We had other volunteers there helping out with traffic. People brought their telescopes. A great night, but with the volume of people we're getting, we'd love more volunteers to come out. It was a really great night. We had a lot of families with young kids who were super interested in all this and really pumped about learning about the night sky. So August the 14th, please mark it in your calendar. Yeah, here we go. So where it is, of course, if you're not familiar, it's at the CARP branch of the Ottawa Public Library, which is right next to the Deafin bunker. Timing is 8:30 to about 11:30. There's the website if you want to know more about it, or go to our website and you can find it there as well. If you are volunteering, if you can be there around 7:30 or 8, that would be fantastic. We're looking for volunteers. Bring your telescopes to help with traffic control, the greeting desk, all that wonderful stuff. If you got any questions, don't hesitate to reach out to Deepinder. His email is starparties@ottawa.rasc.ca. Okay, Fred Lossing Observatory, we talked about it earlier, but as you can see, there's 3 large fixed telescopes there, one with the roll-off roof and 2 in the domes. That's at the Mill of Kintail, and as a member, you are welcome to enjoy these as well. There's a small nominal fee if you're actually going to be using the big telescopes that helps to contribute to the maintenance. I believe it's about $30 a year. Our next member star party out at the Fred Lossing Observatory is tomorrow night by the looks of things. So waxing crescent moon. Let's hope it's not cloudy. I think it's supposed to rain. Our director is Rick Scholes, Stan Mott Book Library. We got John Thompson, who's up here tonight. So if any of you want to check out the library afterwards, please reach out to John. Rich Chen's our other librarian. Ted Bean Equipment Loan Library is run by Peter Shute. Coffee and Conversation, that's a position on council that has remained open if somebody's interested. And RASC membership info, please contact Art Fraser. All right. Thank you for this evening. In the audience, we've had 32 people and 33 on Zoom for 65 attendees. A great thanks goes out to all the presenters and speakers this evening, as well as our host, the RASC National Office, and the Zoom capabilities they provide for us. Any comments, ideas, suggestions, you want to do a presentation, please reach out to meetingchair@ottawa.rasc.ca. Our next meeting is on Friday, September the 11th, same place, 7:30. It's the second Friday next month, just keep that in mind. And just reminders, you head out, the Rescue Museum is closed, so otherwise you get stuck in here at night and they let the dinosaurs roam through the airplanes at night, so you don't want to stay. For the post-show party, it's at Liam McGuire's, for those who are interested, 1705 Saint Laurent Boulevard at Innis. And that's our meeting for tonight. Thank you very much, and have a safe drive home.